So here we go. Problem number 25. Draining a tank. It takes 12 hours to drain a storage tank by opening a valve at the bottom. The depth Y of the fluid in the tank T hours after the valve is open is given by the formula Y is equal to blah blah blah. Find the rate dy dt in meters per hour at which the water level is changing at time t. Okay, first of all, let's visualize this idea. If this is a really large tank and it's really, really full, and you open the valve, what happens initially? It not only rushes out, but it comes out like gangbusters. But what happens is the tank empties. The water slows down because there's less weight pushing the water down, so the water comes out at a different volume. And of course, the faster it goes out, the more quickly the water level is dropping. So we'll start with the idea that Y, which is the height of the water, is given by 6 times the quantity 1 T12 quantity squared. And it would like to know what is the rate at which Y is changing with respect to time, with respect to T. Well, I get that rate by taking the derivative of both sides of my equation. All right? And the left-hand side of this is pretty easy. It's dy dt. Second side, do I have all the rules I need to be able to do this problem? Well, I got a constant multiplier rule, right? I can take the 6 out, and then all I have to worry about is the derivative of 1 minus t over 12 quantity squared. Can I use the power rule here? No. You don't know the chain rule yet, officially.
Expand it.
We can expand it. Lucy?
You could also do 12 minus t over 12 and then do the division.
The quotient rule? I think expanding is probably the better solution. So I'm going to say, what is the derivative with respect to time of 1? I multiply these together, I get t over 12, but then I multiply that by 2, so I get t over 6 plus t squared over 144. How did I get that? Okay, when I expand it, firsts and my lasts, those parts should be easy, right? The middle terms are going to be this term times that term, and this term times that term. Because this is squared, that's going to be exactly the same. So I get in the habit of just doubling whatever that first product is, which would be 1 minus 2t over 12. But of course, 2 over 12 is the same thing as 1 over 6. Okay, can I do the derivative now? Do I have all the rules I need? Sure. How about 6 times derivative of 1 is 0. Don't worry about it. The derivative of t, negative t over 6 is negative 1/6. Now, if you want to, by the way, if you want to think of negative t over 6 as negative 1/6 times t, and then I'm just doing the power rule to that, that's fine. And then this last one is plus, I don't know, 1/72 t. Can you double check that? Power rule, I bring the 2 down, I get 2 over 144, that's 1 over 72. Reduce the power on the t, I get t to the first. Okay, distribute, and I get negative 1 plus 1/12 t. And so there's the answer to A.
That's A. Alright.
Yep.
13 for Lewis.
What's that? No. When is the fluid level at its fastest? Is the question to be. When is the fluid level fastest? Well, if we graph the derivative function, am I in C or B? B.
You're on B, but graphing is C, so we can do it together.
Oh, okay. Graph y and dy dt together. When t is 0, we have -1. And since it's linear, all we need is one more point. How about when t is 12? This is my. Oh, actually, you know what? This is the graph of t versus dy dt. And so up here at 12. So there's the graph as t changes. So when is it going out fastest? At 0. Why?
That's when there's the most pressure. Bring it down.
Because that's when the biggest pressure is. And here the pressure is 0. There's little changes. Changing up. And then part C, what is the graph of y and dy dt together? So we want y on the y on the x-axis and dy dt on the. How would I do that?
Hello.
Okay. Let me see if I can get this straight. So we want y on one axis and dy dt on the other axis. Okay. When t is 0, I have to make a list here. T, y, and dy dt. When t is 0, y is 6. Because you plug in the 0, you get 6. Okay. And dy dt is -1. Suppose we could try another value of t. How about when t is 6? So 1 minus 1/2 is 1/2. 1/2 squared is quarter. You get 6 quarters. But when we're 6 over here, we get -1/2. And let's do in 12.
6. Oh, 0 times 6. 0.
0. The tank is empty. And what do we get for the derivative? Also 0. You know, and as I look at this, the tank question, it's got a t squared in it. You know what that means to me? Parabola. I think the y. See, when y is 6. derivative's at -1. When y is 6/4, which is here, the derivative is 1/2. I think we got something like this. This is the graph of y versus dy dt. And I think it's parabolic, like a piece of a parabola.
No, I messed up.
Graph y and dy together and discuss the behavior of y in relationship to the signs and values of dy dt. And what I'm saying is, maybe better summarized by what we said initially, and that is, when y is really big, the rate is really fast.
Yeah.
And when y is really small, the rate is also very approaches 0. It's like you get to the bottom of the tank and this kind of dribbles out. When y is big, rate is high. As y depletes, the rate gets smaller and smaller until the rate gets to 0. Okay, there's 25. 29. Monthly profit is given. Monthly profit, this is 27. Monthly profit is given.
29.
It's 29?
Yeah, we didn't do 27.
Sorry, 27.
No, 29.
29. Is that better?
Yes.
Okay, so P is profit and X is the number of software packages sold. Okay? Graph P of X. Seems to me like we'd probably want to do that with a grapher.
I tried it. Wouldn't work.
Yeah.
Is it 5 or 50?
It's 50 times 2 to the
Okay.
times 2 to the 5 minus 0.1x.
No, it's 0.01. It's a point. Oh, well, that changed my graph.
That's why it didn't show up at
Okay,
all the
by the way, I'm going to do this the same thing I did the first time I did this, and that is I'm going to try to use the new. Paul, can I interrupt you, please?
Very sorry for interrupting you. That was wrong with me. If I did that again, you have permission to hit me.
I won't hit you.
Bobby.
Will, if he does it again, you can hit him.
Alright.
All right. I don't mean that. You know that. All right. So I'm going to try to use the graphing function again. But what I'm going to try to again, I think the fact that these fractions get really unwieldy, and if we got this new ability to write things in fraction form, I think we should take advantage of it. So 10 over 1 plus 50 to the power of. Oh, I'm sorry.
Times 2.
Get back up here. Down, over, times 2 to the power of, is it 5?
Yeah.
5 minus 0.1 x. So do we have that written right?
Yeah.
Okay, before I just go zoom normal, which is the way I usually have this, first of all, what values of x will make sense here? Are we only going to sell one of these software packages?
No.
Are we going to sell -5 of these software packages?
No.
Okay, so how about we don't even look at values for x of negative values? Okay, what kind of value, what kind of profit do we expect? $1?
No.
Bigger.
Bigger.
More than
1,000.
You're being dead.
Okay, so how about we set our window and we'll go from 0 to 1,000.
That's a lot.
Why not?
10,000.
All right.
What's your scale?
And my X scale, how about by hundreds?
Yeah. Sounds good.
It's crazy.
And then I'm not expecting to make negative money. And so I will put this at 100 grand.
Man, you're swimming in the wall.
And my Y scale,
10,000.
10,000.
Oh wait, weren't those numbers 4 to 1,000? So wouldn't the numbers be really little?
Yeah.
Oh, the profit's already in thousands of dollars.
Yeah.
Okay, so let's take this to 100 then. And let's do this by 10. So 100 is 100,000. And this 10 is really 10,000.
What?
Let's see what we got.
Disappointment.
We didn't make
Show up.
any money.
Dang it.
Made $7.
That looks like
We
the
made
opposite of a
$7.
parachuter.
You didn't enter it.
Just kidding. We made
500.
It seems to the profit kind
We
of.
have a. What's it called? That Numerical thing?
we made about.
Steven?
Oh.
If you go from 0 to 200, and actually you only have to go up about 12 on the Y.
So you want to go 200 here? We're going to go up by 10s? Or 25?
20.
20?
Yeah.
25.
No.
No, it was 25.
And where's the profit max out about?
12. The Y goes up.
10. Just one track higher.
Okay. So what's this telling us? Sounds like at some point, we kind of max out the profit. No matter how many more we sell, we don't make any more money.
It's like that one with bounds and
It's,
that
yeah,
what's called.
actually this is a classic logistics growth model where there's only so much carrying capacity in an environment.
Exactly.
I had that one unlocked.
And we'll revisit this particular curve later in the future. Okay, let's talk about the curve. So we graphed it. What values of x make sense for this problem situation? Only ones that are positive. That's part B. Use the n deriv to graph p prime. For what values of x is p relatively sensitive to the changes in x? Okay, help me through this graphing of the p prime function. Go down here, n deriv, alpha 2.
How do you get the enter?
Well, on the new operating system, it's alpha f2.
What about the really on the old
In the old one, if I get out of here so I can quit.
Math 8.
On the old one, if I want to do an n deriv, it is math. And it's at the bottom of the first list, and it is indeed option A. So n deriv,
What's the order again?
okay, x.
How do you do?
How about y1? Okay, on the old calculator. By the way, now would be a really good time to upgrade your calculator, simply because this new operating system is so much.
What if you
Can I leave
Better.
this here?
Heck no.
I'm going to say the 83, it's time to get rid of it and get an 84.
Why didn't let me?
Yeah,
My
I
brother's in college math and he's away from
I
mine.
could get like 8 of those guys.
Yeah, well,
actually buy these and
How do you do the Y1 thing?
okay. If you're in the old version of the calculator, n deriv has this syntax. It's the function that you would like to take the derivative of, comma, the variable of differentiation, comma, and then the value you want to take the n deriv of. So if you want to put this in your y2 menu, that's what you would put in. Where do you get y1? You get it from bars, y bars, function.
Function 1.
function on my calculator. I'll do it this way.
Yeah, it would cool that.
Need to change the window. Can you barely see the derivative function here?
That's the relative derivative.
Illegal.
Right. So let's change the window, and I really want to change the y value probably to like 1.
Well, because you got rid of your y1. You need to
Okay, there's the profit curve.
Wait, what's our y max?
And the thick curve is the derivative function. Okay.
Oh no, that's just you need to zoom in.
When is a function sensitive? It's sensitive when the derivative is high. When small changes in x cause big changes in y, we call this function sensitive. Where is the derivative going to have that kind of relationship? When either you have big negative numbers or big positive numbers in your derivative. So where is it most sensitive? It's most sensitive when that profit graph was at its steepest slope. At the very beginning, the profit curve was very shallow. At the very end, the profit curve was nearly horizontal as well. Those places, not so sensitive. But in this area here, and what's my scale here, 25s?
Yeah.
10, or 25, 50, so around 100, 110, the function seems to be most sensitive.
Between 60 and 160.
Okay? So between here and here. Oh, I can actually write on this. So between, there's 100. So now I can't draw. Alright, so between here and here. Okay? In other words, places where it's not 0.
I have to guess fuck.
Yeah. I just have to wait until you sit down again before I can resume because the idea that you're standing there and have a conversation with them really distracts me.
Sorry.
All right. So there's 29. What else do we have to talk about in 29?
The max.
When is the marginal profit the greatest? Where it's steepest? And where does that look like it is? Did we say it was about 150? 110?
You say 110.
Is that what they say?
They say 106.
106? Yeah, we're in the ballpark. And then what is the marginal profit when 50 units is sold? Well, wait, marginal profit is the derivative of the profit equation. Can I take this? Do you know how to take that derivative? Do you have the rules for that one yet? Does that mean we're stuck?
Yeah.
No.
No, never stop.
No, I was.
It means if we can't take the derivative symbolically, we should take it numerically. In this case, what is the numeric derivative? How about we use the end derivative function? Math 8. And I'm going to take the derivative with respect to x. I'm going to take it of y1 where I put the profit equation. And I'm interested in its derivative when x is, what, 50? So it says, I'm on part E right now. So what's the marginal profit when 50 units are sold? Well, let me do the end derivative with 50.
$13. Yeah, so isn't that $13?
This is in thousands, and then move this 1, 2, 3, $13.30 per unit.
Is that good?
Oh.
Is that
Oh yeah, that's it, but that's not
Yeah.
right.
I'm sorry?
Yeah, the
We
very
got
fast.
different answers.
I got.
So wouldn't you then
It's
multiply?
supposed to be 13.
This number is in thousands of dollars per unit, right? So if I want to do it in regular dollars, I'd move the decimal place 3 places, and I would get $13.32 per unit is my marginal profit. What if I want to do at 100 units? Second enter, and I go and I'm going to change that 50 into a 100.
164.9.
Move it 3 to $164.94 per unit
So then
is the marginal profit if I'm selling 100. And then second, enter again. And now what they're asking me is what? 125. We can see our marginal profit slipping to the $117.
Didn't make any money at all.
And then my marginal profit for 175. Oops, too many places. $5.88. And then what's my marginal profit at selling 300 units?
Nothing. Is that what expenses to check the profit?
That's where it's like it costs so much to get that one additional sale. Okay, so you think about like what would be an example of that?
You're going farther across the country.
It costs so much to advertise to make the sale, to try to get someone to make the sale, that all the money that you made is spent in the expense of trying to make the sale. So what's the point? All right. So I think that takes care of 29. What is the limit of p of the function p?
10.
Was it 10?
I don't know. That's what the answer said.
yeah, it's 10.
Window. Let's go to 400. And what was my max that we did before? 12? So there's my profit curve. And then I'm just going to hit trace as soon as my derivative curve finishes drawing. Little worm still going there. There we go. Trace. And it looks like it maxes out right around 10.
So wait, they only make like $10,000.
So the maximum amount of profit that we're going to get is $10,000.
Is there gonna be a word problem on the test?
Are there word problems on tests? Sure. Yeah, I hate a lot of things too.
I like math. I just don't want applying to like I'm good at it when we're just like doing math, but like I'm not good at pulling things out. I like I just like chilling with my bros and doing math, but I don't like chilling with my bros and doing like math.
It's only go up.
Let's
Go find some derivatives.
Let's find some derivatives.
Okay, number 33. Number 33, a few years ago, a guy parachuted 179 feet from the top of the Tower of Pisa. Make a rough sketch to show the shape of the graph of his downward velocity during the jump. This is one of those things where you have to sort of apply what you know. Here's what I would imagine. If we're going to do a graph of his velocity as a function of time, that at the initial point that he's jumping, he probably has a really high velocity. Well, sorry, it's probably this way. It goes up, and then he pulls the chute. And he what? He starts to slow down. And then at some point, his parachute
Breaks.
Okay. No, what usually, you think about, he jumps, his velocity's going up, the parachute opens, he starts to slow down, and ultimately he slows down to the point that when he hits the ground, he's got a velocity that will not kill him.
But won't he go up once it opens?
No,
Force there.
no,
You think of real
no.
life.
When you open your chute, you do not go up. Now, if you've seen those movies when people are skydiving and they open their chute and they look like a shoe up, that's because you got a cameraman here and a parachutist here, and they're both falling at the same rate. This person opens their chute and they slow down, but the cameraman continues to go down. They're both still going down. It's just that this rate is slowed down so much it appears to shoot upward. It's an illusion. People do not go upward in parachutes. Otherwise, you jump out of the plane, you open the parachute, and then you what? You rise until what?
You die. And the atmosphere is out here. Everyone might be.
Okay. Yes.
It was the answer, the possible answer was like
Yeah,
really
it doesn't look right. It looks wrong.
No, it wasn't.
It looks so contact makes me cool.
It was basically the same thing going up and then going down.
No, it was like
That's what it looks like.
Okay.
This?
Yeah.
Terrible.
I mean, not going up. Well, kind of.
Doesn't actually.
You just described that as.
Yeah.
It's going
How do you spell that? Oh, you know what? Okay. Here's the point.
Yeah, that's.
Okay. You know what? Here's their point. Here's the guy standing on the top of the. He's standing on the top of the Tower of Pisa, right? How fast is he moving? Just before he jumps. He's not moving at all. At the moment he jumps, at the very moment he jumps, he's got no velocity. Then what happens? The velocity
It's really fast.
goes up fast. Then he opens the chute.
Then it slows
Then
down.
his velocity
Is his velocity
declines.
that high when he jumps? So it's the like equivalent.
You're going pretty fast.
Oh, it's just gravity. So he's falling.
This is during the free fall.
Oh, alright. I thought you were talking about him jumping off the plane. I'm like, wow, he can jump high. Why did he just jump and skydive?
This is a no Tom Petty zone. This is the same. All right. So his initial velocity is 0. He's in a free fall, so it's the same sort of parabolic speed. Actually, the path is parabolic. The speed is linear.
Like, pretty much.
He's got a linear increase in speed until he opens his chute,
The next one.
and then he has a decline until he can, hopefully again, slow down enough that he can hit the ground without killing himself. Phil, and then
Or breaks. He hits the ground really hard and dies.
And then you can go faster.
So how does it work?
because objects in free fall all fall at the same rate. If you ignore friction, parachutes open, causing lots of friction, and the friction slows the descent. In a vacuum, the parachute will not help.
Wait a minute.
There's no air.
I have the same issue. It's that acceleration is constant, not velocity.
Acceleration is constant.
This is a velocity versus time graph. So the velocity would increase because the acceleration is constant.
acceleration is constant. The velocity which something is, there's more than just the acceleration due to gravity at work here. We realize that.
Well, but for the free fall. I'm just talking about that segment.
Okay, hold on. Correct?
Yeah.
This is the derivative of velocity, right?
I see.
So what would have to be my velocity equation such that if I took the derivative, I got this? And what would be my position such that if I took the derivative of that, I would get this?
That's linear. You're right.
So the position is parabolic, the velocity is linear, and the acceleration is constant. All right. So you're saying during the free fall, you were saying no. The free fall, the velocity grows linearly. Okay, I think we've done enough to that. What kind of idiot jumps off the Leaning Tower of Pisa anyway? That's what I'd like to know. Okay, last one, 37. The position x-coordinate of a particle moving in a line on the line y equal 2 is given by.
Have you seen? This is this isn't like an irrelevant question. It's about how math applies to like real world. Have you seen A Beautiful Mind?
I have not actually. I have not seen that movie.
Okay, well, like in the beginning, like he looks at he looks at like a reflection or something.
Bringing up Robin Williams movies, dude.
It's not even in that movie.
It's Ben Affleck and Robin Williams.
No, you're thinking of Good Will Hunting. Different mathematician, crazy movie.
It's really like applied math. You can see like applied the reflection of like light.
Oh yeah, it's the
to
guys
some oranges. Yeah, it's like to like look at something high.
And the answer.
equation for how clear your time is.
Oh.
How what?
Well, you have to grade it that the subject of that movie took the application of math to great extremes. You know, he attacked everything like a math problem, including, when he was at his worst. From my, again, I haven't seen the movie, but I've read a bit of the biography of this person. Whenever he'd see a situation, he'd have to sit down and calculate the probability of that situation happening by total random chance. Okay? Now, that is an extreme thing. But yeah, almost every situation can be thought of, especially things that are in the physical realm. And if you ever seen any of the addendum materials for looking at Pixar movies and how Pixar movies are created. The mathematics of light reflection, like you were talking about with the orange and the tie and there. I mean, the mathematics behind those things to try to digitally create shadows. And how light, my eyes look the way they do, not because my eyes are a certain color, but also because my eyes are reflecting the color of my shirt. And these things happen all the time, and they're mathematically quantifiable, but we probably should not forget to live as we look, as we deal with how life can be quantified and broken down and stuff like that. Can I get the last problem? Yeah. Last problem. So we've got a situation where a particle is moving using these parametric equations.
Oh no.
And at any time t, I can figure out where it is in the x value, and at any time t, I can tell you that it's going to be at y equal 2. So essentially, I have a graph, x and y, and this particle may start here, and then move at some new time t, and move backward, and move forward, and do all sorts of things along that line, y equal 2. Okay? The question that they ask is, describe the motion of the particle for when t is greater than 0. Well, what could we say? we could say, well, where is the particle when t equals 0? Oh, I think its x value is -5. I think its y value is 2. And by the way, I think it's going to be 2's
All the way down.
all the way down. All right? What happens as time goes on? Does it move to the right or does it move to the left?
I don't know.
Does it stay still? This is where the calculus will allow us to get some insights. I'm interested in x prime of t, the velocity that this particle is moving in the x direction. And when I do that, I get 6t squared minus 26t plus 22. That's a quadratic. Does this factor at all?
I think.
Yeah, you can pull it.
I can pull a 2 out. 2 times 3t squared minus 13t plus 11. Does that factor as 3t and t?
What did you
Plus,
can't
it
do
doesn't.
nothing?
It doesn't.
Yeah.
Well, 11 times 1.
And then it's 13.
That doesn't up to 13. Do I have the right equation?
So you can, you can multiply the 3 part by the 1 part to get 3.
Yeah, but when I add it to 11, I get 14 out
Oh
here.
yeah.
Okay. So it doesn't factor. So what do we do next?
Quadratic.
Quadratic.
No, it's just like.
When will this equal 0? This will equal 0 when, let's see, t is equal to negative 13 plus or minus b squared, which is 169, minus 4 times 3 times 11, all over 2 times 3. Ready for that part? Okay. Oh, okay. Great if someone solved that for me while I'm doing this other thing.
What?
13 plus or minus 4 times 3 is 12. 12 times 11 is 132.
Yeah.
So this is 169 minus 132
7.
over 6. 13 plus or minus, what's 169?
37.
Square root of 37 over 6. Yeah. At this point, I think we switch over to approximately. So I need 13 minus
Plus 3.18.
what?
The plus is 3.18.
3.18,
The minus is 1.15.
1.15. I need 3 decimal places on both of them.
152.
152,
180.
180. Okay, and I do that because the standard for the AP exam is 3 decimal places. So here's what I've got. I know that I'm starting here. I know that I'm starting at negative 5, 2. I'm over here. Okay? These two places, sorry, those two times are where the velocity is going to be 0. Between time equals 0 and time equal 1.152, I can only be moving one direction. And I believe that direction is going to be positive. Discuss. How do I know that the velocity is positive between 0 and 1.152?
Going to the right.
It's a cubic between 0.
Well, don't think about the cubic. Think about this.
Oh.
That's a parabola.
No, it can't fit 2 times.
That's a parabola that points
That was my second
up.
choice.
Is it?
That's a parabola that points up and has 2 roots. So I have a parabola with 2 roots that are pointing up. Before the first root, it's got to be positive. Between the first and the second root, it's got to be negative. Negative velocity between those 2 times. And then afterwards,
It goes to positive.
it goes back to positive again. So what I'm seeing is that this particle is moving this way. It's going to come to a stop. It's going to change direction when the velocity is negative. It's going to come to a stop again. And then it's going to continue on its path, moving always positive from there on out. That's what I think.
I think you're right.
I agree with you.
Let's check my answer.
I said we bank on it.
Let's check my answer. Mode. Parametric mode.
We'll take it anytime.
That's a must. Okay, so I've switched to parametric mode. What was my equation? Some big thing. Thank you.
2t minus 13t squared plus 22t. I'll try and guess. 2t minus 13t.
No, wait.
Oh, sorry.
This is the downside. Wrong.
That's not you.
T cubed. Arrow to get back down. There we go.
Minus 13t squared plus 22t minus 5.
Just in front.
That doesn't sound like calculus you're talking about over there. This is actually a start.
Oh, I'm sorry.
So
It would be helpful by plugging a Y. It'd all be helpful.
I knew it.
Let's do this going up to like 10, 12. All right.
Wait, you had 22 as. Wow.
Hold on.
You had the 22. He says 22 at the end. It should be 11. Oh, sorry. I can't see.
Oh yeah, it should be 11.
It should be 11 at the end.
In the end, you factored out the 3.
We factored it out.
No, I'm putting in the original position equation. Now, what I did to manipulate to get the velocity, and when the velocity was 0, is another question. But this is the original thing, and what we say is, we think it starts at -5, it moves to the right, it moves to the left, and then moves back to the right.
Yeah.
That was so
That's some retrograde motion right there.
Tyler, this was fine, Emily.
Now, what you just informed me, because I did exactly the same thing in the parametric section from the recordings I made over the summer for chapter 1, that wasn't supposed to be a surprise. You knew about the little football thing with parametric equations. At least you should have.
I did not.
All right.
Yeah.
But what did we see? You saw the particle move to the right, the velocity turned negative, it moved to the left, the velocity turned back positive, it moves to the right and keeps on going. Okay. When does the particle speed up or slow down?
It doesn't.
Now when it changes direction.
No, when it goes to the left, it slows down. It's the ginger L.
Find acceleration.
Like 5. What?
When does it speed up? Okay, a question. It speeds up when something speeds up when it's accelerating. Well, this is really this is problematic language for us here.
Because acceleration is
Okay, let's go back to here for a second. Here's our velocity right here, right? There's our velocity. Okay, go ahead. All right. I think I need a new slide here.
Go, Tyler, go.
3 off.
Everyone look
Is a scarf slowing you down or something?
Hey, it looks very good on him.
I gotta admit it, right?
Okay, going back to where we here. I took the derivative, I got the velocity. The velocity ends up being a quadratic. The quadratic graph is parabolic. We solved the parabola to find its two roots, and one of them was like 1.1, 1.153, and the other one was a 5 point.
No, it was 3.512. 5.2.
It was 3.182.
Yeah.
3.8118.
No, 182.
Okay. Now here's the problem. When is something going faster? When is it speeding?
Moving away from zero.
When it's moving away from zero.
Moving away from the x-axis.
Moving, yeah.
Okay. Here's okay. Let's look at this velocity. Here, velocity is 0.
And then it's going in the other direction.
Okay, hold.
I'm
Okay.
jumping ahead. Sorry.
Would you say it is for this part of the curve?
That's negative.
going right.
For this part of the curve, is it speeding up or slowing down? So this is slowing down. Because I'm going at a speed and my speed is decreasing. Sorry, my velocity is positive and I'm decreasing.
Yes.
Okay. For this part of the curve,
Speeding up.
Speeding up.
I'm speeding up. Why?
Because
I was at 0
You're going away from 0.
and I'm getting more and more negative.
That's right.
it's increasing, not increasing.
Speeding or slowing down.
Slowing down.
I had a negative velocity,
Increasing.
but my negative velocity is now coming closer and closer to 0.
You know.
Now, with all of that drawn in, we need a basic set of rules that allows us to say when is something speeding up.
Moving away from the x-axis.
Okay, I need it in calculus notation form, please.
Limit as x approaches 0.
When velocity when velocity is positive and the rate that velocity is changing is negative, that's this.
Yeah.
That's slowing down. Velocity is positive, but the rate of change in velocity is negative. When velocity, let's do the other slowing down. When velocity was negative, and the rate of change in velocity was positive. Those are my two slowing down situations.
So it's on the velocity times the
Speeding up is when velocity is positive and the change in velocity
It's greater than
is also positive. That's this one right here. Or when velocity is positive, that's supposed to be positive, or sorry, negative.
it's negative, but it's greater than 0.
Velocity is negative, and the change in velocity
It's less than 0.
is also negative.
Oh, oops. I was reading my
So, speeding up happens when velocity is negative and acceleration is negative. Or when velocity is positive and acceleration is positive. So a free fall projectile. I drop it. Is it speeding up?
Yes.
Okay, what is the acceleration? 9.8 negative.
9.8.
And the velocity is also
Negative.
going down.
Yeah.
I take a projectile. I throw it in the air. On the initial throw, what's going on? Velocity is positive, but acceleration is negative. That object is slowing down.
That's
The,
crazy.
the object reaches its apex. Then what happens?
It starts falling.
It starts falling in the same direction as acceleration. So, things speed up when velocity and acceleration are in the same direction. Things slow down when velocity and acceleration are in opposite directions. And remember, acceleration is the slope, the derivative of velocity. All right. So that concludes my coverage of the 3-4.
They're both. We did it. Like they're speeding up when acceleration and velocity are what?
Yeah, I thought there was more than